Welcome to Lecture 3.7, the Euclidean algorithm. The Euclidean algorithm computes the greatest common divisor of two integers. So let's start with a definition of that. Let's let a and b be integers. They both can't be 0, but one of them can. The greatest common divisor of a and b, denoted the GCD of a and b, is the positive integer d, satisfying the following two conditions. First off, it has to be a common divisor of a and b, which means that d divides a and d divides b. And second is the greatest part. Namely, if c also divides a and b, then c is less than or equal to d. So any other common divisor has to be no more than d. In other words, for all natural numbers c, if c divides a and c divides b, then c is less than or equal to d. Now I should mention that a few other sources, it's common to replace this condition, c is less than or equal to d, with a weaker condition, something that seems weaker, that c divides d. And same down here. But these conditions are actually equivalent. Let's do a few simple examples. First of all, the GCD of 72 and 63 is 9, because 72 is 9 times 8 and 63 is 9 times 7. The GCD of 10 to the 12 and 6 to the 18th is the GCD. Let me just factor this a little bit. 2 to the 12 times 5 to the 12, and 2 to the 18 times 3 to the 18. So notice that this 2 to the 12 comes up, that's the largest factor of both of these, so that is the GCD, 2 to the 12. Next, the GCD of 5 and 0. I claim this is equal to 5, and let's see why. Let's go over here. So 5 divides 5, and 5 divides 0. Everything non-zero divides 0. So that's the GCD. Notice that the GCD of 0 and 0 is not going to exist. So actually I said notice, let me explain that. Does not exist. First of all, I did not allow that in my definition, but even so, remember that in a previous lecture we talked about divisibility. Now it makes sense to say that 5 divides 0, but it does not make sense to say 0 divides 5. 5 divides 0 because 0 equals 5 times something, namely 0, but 5 does not ever equal 0 times anything else. And we also mentioned that not only does, so we said 0 does not divide into anything, and also we did not want to allow 0 to divide into 0 either. We could, but I think it just opens up too many problems. It causes more problems than it solves. And it all has to do with the fact that 0 divided by 0 is not defined either. Let's now do a lemma which is really at the crux of why the Euclidean algorithm works. So this says if a and b are integers and they're both not 0, and q and r are integers that satisfy a equals bq plus r. So think of taking b and dividing it into a, and q and r the quotient and the remainder. Then the GCD of a and b equals the GCD of b and r. Now this is actually a little bit more general than this because b is allowed to be 0, and as I've already said, we can't divide 0 into a, but if b equals 0, we can still write a equals 0 times any number q for any quotient, plus the remainder, which is going to be a. Now we don't normally allow, the reason, well, general q and r are unique, so in this case they are not, and that's why when we introduced this a few lectures ago, we did not allow b to be 0, but in this situation we can notice that q does not occur in this equation, so it's harmless to say that either one of these can be 0 as long as the other one is not 0. Okay, so why this is important is because typically a and b might be big numbers, and if we want to compute the GCD of two big numbers, well, if we divide one into the other and get a much smaller remainder, then we can simplify that by computing, then it's easier to compute the GCD of two smaller numbers, say b and r. And then we can recursively do that, and eventually we run out of numbers because they get smaller and smaller, and then we can just do it by hand. Let's get started. To show the equality of these two numbers, the GCD of a and b, and of b and r, we'll show that the first number is less than or equal to the second one, and then vice versa. So to begin, let's show that the GCD of a and b is less than or equal to the GCD of b and r. So here's how we'll proceed. We'll take an arbitrary common divisor of a and b, let's call it c, and we'll show that it's also a common divisor of b and r. What that tells us is that the greatest common divisor of a and b, that's the largest common divisor, is also a common divisor of b and r. So it can't be any, by construction, by definition, it's not bigger than the greatest common divisor of b and r. And that's the equality that we seek. So let's write that down. So let C be any common divisor of a and b. So then C divides A and C divides B. So that means that, so let's suppose that A equals, let's say C times K, and say that B equals C times L for some K and L that are integers. That's what it means to be a divisor of for C divides A, that means A equals C times some integer K, and similarly B is C times some integer L. Okay, so now what? Now we're going to take this equation A equals BQ plus R, and we're going to just plug these new values for A and B into here, and we'll solve for R. Okay, so then A equals CK equals, I'll just write, I'll write CLQ, that's B times Q plus R. So here's what we have, and now we are going to solve for R. So R equals CK minus CLQ, which is K minus LQ times C. So C times something equals R, and that means that C divides R. So C divides R, and we've already said that it divides B, so it's a common divisor of B and R. Okay, so thus all common divisors of A and B are common divisors of B and R. So the GCD, the greatest common divisor of A and B, is a common divisor of B and R. So by construction, or just by definition of what the greatest common divisor means, if this is a common divisor of B and R, then it has to be less than or equal to the greatest common divisor of B and R. And that's exactly what we wanted to show with this direction. Next, we need to show the reverse. And this really is almost the same. I think I'm going to go through it, but I'll go through it quickly because it really is analogous. So let me use black this time. So now I'm going to let C be a common divisor of B and R. And that just means that C divides B and C divides R. I really should be leaving this as an exercise, but I guess I'll summarize it. So I'm going to let, so if C divides B and C divides R, then I will let B be, let's use different letters so we don't get confused. C times X and R be equal to C times Y for some X and Y that are integers. Then once again we're going to go up to A equals BQ plus R, but now we will write, let's see, so we're subbing in for B and R, so we'll probably be solving for A. Let's see if that works. So A equals B, which is CXQ, plus R, which is CY, which is XQ plus Y times C. And so this tells me that C times something equals A, C divides A. So C divides A. So C is a common divisor of A and B. So C is a common divisor of B, R, and now A. So once again, C, if you take the GCD, the greatest common divisor of B and R, we just showed that that is a common divisor of A and B, so it must be less than or equal to the greatest common divisor of A and B. So I'm not going to write that down, I just said it. It really is the same argument as this. I think I'm ready to put an end of proof box here. So thus GCD of B and R is less than or equal to GCD of A and B. Okay, let's move on. Let's once again return over 2,000 years ago to the ancient Greeks and revisit Euclid. Remember, we saw him when discussing axioms of geometry, but now something else that he did around 300 BC in his famous book called The Elements. He described what is now known as the Euclidean algorithm. And this, in his own words, was given two numbers not prime to one another to find their greatest common measure. So he called it measure, and he phrased it, what sounds funny to us today, despite the translation, but it was a book containing a lot of instructions. So instructions for how to find the GCD, but also how to do things like bisect an angle or do other ruler and compass constructions. This algorithm works due to two key observations. The first one's very simple. If A divides B, then the greatest common divisor of A and B is A itself. And the second one is the lemma that we just proved. If A equals BQ plus R, then the GCD of A and B is equal to the GCD of B and R. This is best seen by an example. So we will let A be 654 and B be 360. And the idea is we will, to compute the GCD of these two numbers, we will divide 360 into 654, take the remainder, which is going to be smaller, and compute the GCD of the remainder with B, and then repeat that process. So if we do that, we get that 654 is 360 times 1 with a remainder of 294. So this is the quotient, this is the remainder. So the GCD of 654 with 360 is equal to the GCD of 360 and 294. Now we're going to repeat this process, but instead of these two numbers, we're going to use these two numbers, 360 and 294. So if we divide 294 into 360, we get a quotient of 1 and a remainder, this one I think you can do in your head, of 66. So 360 equals 294 plus 1 plus 66, and the GCD of 360 and 294 is equal to the GCD of 294 and 66. So we repeat this process. We divide 66 into 294. I think we get 4 or something. This one I can't do in my head, but I do have it right here. 294 equals 66 times 4 with a remainder of 30. So the GCD of 294 and 66 that we were trying to compute is equal to the GCD of 66 and the remainder 30. Keep going. Divide 30 into 66. The quotient is 2, the remainder is 6. So the GCD of 66 and 30 is equal to the GCD of 30 and 6. Now notice we're to the point now where 6 divides 30. So now we're going to use our first property. So here if 6 divides 30, then the GCD of 30 and 6 equals 6, and we're done. So let's write that out. 30 equals 6 times 5, so the GCD of 30 and 6 is 6. We conclude that the GCD of the original two numbers, 654 and 360, is also equal to 6. Let's briefly state the pseudocode of this algorithm. So this is the modernized version, because this is not how Euclid would have stated it. So the input, we have two integers, a and b, that are both non-negative, and one of them, let's just call it b, is allowed to be 0, but not both. We can initialize them by setting little a to big A, little b to big B, and little r to big B. And then we begin the following process as long as b is non-zero. First, we compute the remainder of a divided by b, so that's r, which is just a mod b. Then we redefine a to be what b is, and we redefine b to be r, and then we just repeat that process. So here's the end of the while loop. And then at the end of the day, the GCD is whatever a is, and we return that. Now notice that if we begin with b being 0, then the GCD of positive integer and 0 is just that positive integer a, so we skip this while loop altogether and we return a right away. In the remainder of this lecture, I will show you how the GCD of a and b can actually be written as a linear combination of a and b like this, ax plus by, and then we will extend the Euclidean algorithm to show how to construct such an x and y explicitly. Okay, so here's the proposition. Let's let a and b be integers, as before. Both of them can't be 0. And let's let d be the GCD of a and b. And d is the smallest positive integer that can be written as ax plus by for integers x and y. So what this is saying is a and b are fixed, and we can let x and y be any integers we want to. The smallest positive number that we can achieve is actually the GCD. Okay, let's see why this is true. To prove it, let's first define the set S consisting of all numbers that can be written like this. ax plus by. So formally it's a set of all u, where u is a positive integer, and u is ax plus by for some integers x and y. And we'll let c be the smallest number in this set. Our goal, obviously, is to show that c is equal to d, because that's what we claimed up here, where d is the GCD. I'm just writing it with d to save space. Once again, we'll use a technique that we used earlier in the lecture, that is showing that c is greater than or equal to d and also less than or equal to d. Okay, let's get started. So how do we show that c is greater than or equal to d? Well, we'll show that d actually divides c. So d, what do we know about d? D is the greatest common divisor of a and b. So let me write that down. So I claim that d divides c, and if we show that, we're done with this part, because these are positive integers, and if d divides c, it must be smaller than or equal to. Okay, so we know that d is a divisor of a and b. So let's write that down too. So since d divides a and d divides b, then we can write a as d times k and b as d times L for some, I should maybe put a colon here, just to know how to parse it correctly, for some k and L that are integers. Okay, now what? So our c, which we know we can write like this, so write c as ax plus by, and now let's plug in our new values of a and b. So this is dkx plus dly. Well, let's factor out a d. D times kx plus ly. So now we have explicitly written c as d times an integer. So that shows that d divides c. And that establishes this first inequality. Okay, let's do the second now. How do you think we're going to prove that c is less than or equal to d? What about this? D is a common divisor of a and b. It's the greatest common divisor. So if we can show that c, remember, is the minimum element of this set, also divides a and b, then by definition it must be less than or equal to d, the greatest common divisor. Let me write that down. So I claim that c divides a and c divides b. And this time I don't think I actually need to write out that a is c times k and b is c times l. I could, but I don't think I need to. So what we're going to do now is, so showing that c divides into a is completely analogous to showing that c divides into b. If we do one of them, the other proof is exactly the same. So all we really have to do is show that c divides a. So let's divide c into a, and we'll show that the remainder is 0. So let's write a equals c times q plus r, where r is between 0 but strictly less, greater than or equal to 0 but strictly less than c. And our goal is to show r equals 0, because that will imply that c divides a. So if we can show r is 0, we're done. So here's what I'm going to do. I'm going to show that if r is non-zero, then it can be written like this, ax plus by, and so it must be an S. But that's impossible because S is the set of all, or because C is the smallest element in S. Okay, so let's solve for R, and then so solve for R above, and we get R equals A minus C Q. And now what do we want to do with this? Well, C we know we can write, so C is in this set, so we can write C as ax plus by. So let's do that. Let's write, this is A minus ax plus by times Q. Okay. And now I can rearrange things and I can write this as A times, is it 1 minus xq, right? 1, and then there's ax times q, and then we have a minus b times yq. So notice I have just written r as a times an integer plus b times another integer. This, it's negative what I boxed. And so that means that R is, well, if R is positive, it is in this set S, because S is a set of all things that can be written as A times something plus B times something else. All positive integers. So if R is positive, it's in here. But it can't be in here because it's less than the smallest thing in there, which is C. Therefore, R has to be 0. So, so R is in S if it's positive, but R is less than the minimum element of S. So that means that R must be equal to 0. And so that confirms that indeed C divides A, and I will say that the proof that C divides B is completely analogous. And I should probably say that below, but I'm really running out of room down here. So once we confirm that C divides A and C divides B, then C is a common divisor of A and B, so it is less than the greatest common divisor, which is D. Okay, I think I'm ready for the end of proof box. On our last slide, I will show you how to modify the Euclidean algorithm to actually construct what such an x and a y have to be. And we do this by keeping track of extra information when doing the Euclidean algorithm. And in that sense, it's sometimes called the extended Euclidean algorithm. We'll do our same example using 654 for A and 360 for B. And we'll do an example of this later in the course when we study cryptography, because it's particularly useful when two numbers are relatively prime. That means their GCD is equal to 1, which is not the case here. Okay, so once again we call this the extended Euclidean algorithm because it's basically the plain old Euclidean algorithm, but we're just keeping track of extra information. So throughout, we're going to have these two columns, one for A and one for B. I'll show you what we'll do with those soon. But the first step is the initiation. So what we're going to do is we're going to take both the value of A and the value of B and write them in a column. We'll write something that's very obvious. 654, which is A, is 1 times 654 plus 0 times 360. And we will put these values 1 and 0 in the columns under 654 and 360. Next, we do B. 360 is 0 times 654 plus 1 times 360. So we put these coefficients, 0 and 1, in the columns under 654 and 360 as well. So that's the initiation. Now let's begin the algorithm. Remember how we do it? We divide 360 into 654 and we compute the remainder, which you may remember is 294. So 654 is 360 times 1 plus 294. So we will solve for 294. This is what we always do. We solve for 294. That means we're going to move this to the left-hand side, and we'll write 294 is 1 times 654 minus 1 times 360. Okay? So now what do we put here? It's not quite as simple as putting a 1 and a negative 1 here. What we're really doing is we're saying 294 is 1 times 654. So here's 654. We take one copy of that row, 1, 0, and we subtract one copy of the 360 row. So we subtract, here's 360, we subtract minus 1 of that row. And so this row, 1 times this row minus 1 times that row gives us 1, negative 1. Okay? Let's keep going. Remember the next step? We divide 294 into 360, and the remainder, if I remember right, I think it was 66. So 360 equals 294 times 1 plus 66. That's the remainder. So we always will solve for the remainder, move the b over to the left-hand side, and we get 66 is 1 times 360 minus 1 times 294. So once again, this 1 here, 1 times 360, there's the 360. That means we're going to take this row and multiply it by 1, and then minus 1 times 294. That means we're going to take the row for 294 and multiply it by negative 1, and we're going to add these together. So it's the same thing we had before. 1 times this row minus 1 times that row. So entry by entry, we get 0 minus 1 is negative 1. And then in the second column, 1 minus negative 1 is positive 2. Okay, got that? Now we keep going. We divide 66 into 294, and I think we get 4 with the remainder 30. So 294 is 66 times 4 plus 30. So once again, we solve for 30. We move the 66 to the left-hand side, and we get 30 is 1 times 294 minus 4 times 66. So this 294 is this row up here. So we're going to take one copy of that row, and we will subtract 4 copies of the 66 row. So that's the row up here minus 4 of these. So what does that give us? 1 minus negative 4 times, or I should say 1 minus 4 times this row, not negative 4, is 1 times 1 plus negative 4 times negative 1, which is 5. And similarly, 1 times negative 1 in the second column is negative 1 plus negative 4 times 2 is negative 8. So that's negative 1 minus 8 is negative 9. And we keep going. So let's divide 30 into 66. We obviously get 2 with a remainder of 6. So 66 equals 30 times 2 plus 6. So we solve for 6. And we move the 30 over, and we get that 6 equals 1 times 66 minus 2 times 30. So the 66, that's this row. So we take this row, which is negative 1, 2, and multiply it by 1. And then we add negative 2 copies of the next row, 30, which is, I didn't write my negative sign, negative 2, which is 5, negative 9. So if we do that, we get, in the first column, 1 times negative 1, plus negative 2 times 5, which is negative 10, which is negative 11. In the second column, 1 times 2 is 2, and negative 2 times negative 9 is 18. 2 plus 18 is 20. So you get the idea? We can keep going with this. Let's see what happens when it terminates. So the next one, of course, 6 divides evenly into 30, so 30 is 6 times 5. And now we're done. So what does this tell us? Well, our final coefficients are negative 11 and 20. And, well, I claim that the GCD of 654 and 360 is equal to 6. We've already established that. But moreover, these coefficients right here, negative 11 and 20, tell us how to construct 6 from a linear combination of 654 and 360. So namely, the GCD is 654 times negative 11, these two numbers, plus 360 times 20. So I encourage you to pause the lecture at this point and go back and see if you can reconstruct where that came from these, I almost want to call them row reductions because it's a lot like what we do in linear algebra. Okay, so are you back? Why is this nice? Well, one reason is that if you're asked to solve a problem like this, now you know how, but more generally, if we have equations of the following form, like 654 times x equals 6 modulo 360. Now I've briefly talked about mod, but what this means is that we want to find some number x that has the property that 654 times x, if you compute the remainder of that mod 360, it's the same as 6 mod 360, which is just 6. So how do we compute something like this? Well, notice that from this equation here, 6 equals 654 times negative 11 plus 360 times 20, that if we divide 360 into both sides, then this term goes away because of that 360. We get 0 here, so all that counts is these two terms. And this, negative 11, this is precisely the x that we need. 654 times x is equivalent to or equal to 6 mod 360. And we'll talk more about modular arithmetic in a couple of lectures. I know I've briefly talked about the remainder and how we call that mod. I haven't actually formalized modular arithmetic, though I know a lot of you have seen it before, and we all use it on an everyday basis when telling time. I mean, hours in the day are like mod 12, right? Because if it's 10 o'clock and you sleep for 4 hours, then you wake up not at 14 o'clock, but at 2 o'clock. Okay, so an equation like this we can solve, and we get that x equals negative 11, which is the same, remainder 360 is the same as 349. Sort of like how 1 hour before midnight is also 11 o'clock. So 349 is 360 minus 11. So we can also solve 360x is equivalent to 6 mod 654. Let's see how to do that. So given this equation, what happens if we divide 654 into both sides and take the remainder? Well, this term goes away because this is a multiple of 654, and we're left with 6 as the same remainder, mod 654, as 360 times 20. So 20 is the x that we seek right here. 360 times 20 is equivalent to 6 mod 654. There we have it. And this type of equation is what we will need to solve when we study cryptography, which will come up later in this course. And normally in that situation, what we actually have here is, for reasons that we'll understand later, is not a 6, but a 1. And that comes up because our numbers a and b are relatively prime. And so that's going to give us a 1 right here. Okay, so a lot of fun stuff coming up. Stick around.